So we are talking about chemical equilibrium today. Our objectives are to figure out the difference between reversible and irreversible changes, what dynamic equilibrium means, talk about an equilibrium constant, K, we'll learn about that, and then make calculations involving this equilibrium constant and some concentrations. So I want us to be able to talk about what a reversible reaction and an irreversible reaction are and what conditions might determine whether it's reversible or irreversible. I want us to talk about whether or not something is going to have the same rate if it's in a forward reaction or a reverse reaction. I want us to understand what a balanced equation is going to do to help us make an equilibrium constant. And then I want us to take that equilibrium constant K or our concentration, and then we're going to actually do a calculation, and we'll see how that works. All right, so we know that there are some things that are reversible reactions, some things that are non-reversible reactions. Things that are going to completion, like if I'm taking some iron and I'm rusting the iron, we're not really going to see that thing go back very much to the other direction. Okay, now all reactions in theory, under the exact right conditions, could be reversible. But what we see in reality, partly due to some of the stuff we learned last unit with Gibbs free energy and things like that, is that some reactions are going to be favored to go to completion. Other reactions might be more reversible. Things like combustion would be a good example of something that's probably going to go to completion. If I take that match and I light that match and I turn it on fire, it turns into this pile of ash. It's not likely going to go back to something that's a piece of wood again, unless some really crazy environments, really crazy conditions we're able to do that, right? And so reversibility depends upon conditions. How reversible it is might depend upon the concentration, the pressure, or the temperature. So the reversible reactions could be things where you would end up taking like a copper sulfate and hydrating it and then dehydrating it. Maybe taking your ammonia and your hydrogen and turning it into, your nitrogen and your hydrogen and turning it into ammonia. Those would be good examples of reversible reactions. So let's say I had like an N2 plus an H2 is going to turn into NH3, right? That might be a good example of a reversible reaction. And you'll notice that I'm going to put a double-sided arrow when I use that reversible reaction. Okay, so we'll talk about some of these types of situations that we have. So our reactants are turning into our products. Our forward rate is going to be equal to our reverse rate. Now notice that it's not going to be an equal concentration, okay, but it might be a constant concentration or constant change. So the amounts of the products and reactants that are changing into each other will be constant, but it doesn't necessarily mean that the concentrations are equal. And you guys are going to do a lab later on that will be a really great example of this. And it's so simple, it's just moving paper clips around, but it's just a brilliant way to demonstrate that the concentrations are not necessarily going to be equal, but you can have a constant back and forth. So the rate of the forward and the reverse reactions are going to be equal. Remember that there are changes. It might seem like there are no changes. There are changes, right? It just is that there are no net changes in the amount of your reactants and products. And so the amounts are changing. Now we will use double arrows, and you can use an arrow going forward and an arrow going back. You could use the double-sided arrow, like that double-headed arrow that we just saw up in there. And my favorite is to do something that has like a little half arrow on both sides. And any of those would be good indicators that you have a reversible reaction and it's going in both directions. That is an equilibrium condition where you have equal rates. Questions on that? Okay, so we saw this picture before, and I want you to look at that picture and raise your hand if you think you can tell me when we first hit equilibrium. We did this before earlier on in the year, but you might not remember it. Can you tell when we first hit equilibrium? Okay, I'm going to call on somebody. We'll call on antimony. Okay, no guess. We'll call on bromine. What is it? CYC. It looks symmetrical. What do you mean by symmetrical? Okay. I'm liking C. I'd like a little better description. Bismuth, can you give me more? Okay. How about livermorium?
I was kind of thinking that it was like proportional. So like the first two are like connected and are like bonded, and then there's one bonded, and then the other two that are unbonded like can still be bonded, and I feel like that's like equal, like totally, like
Okay.
whole. If you like look at how many bonds can be formed.
Okay. I think you might be getting close to the answer. We have not stated it the way that it needs to be stated, but you might have an inkling of the correct idea. Arsenic. Okay. Good guess. Let's see. You are gallium. Is that right?
When like four compounds are like have three bonds, and then the other three have like 5 bonds. Or yeah, and that's like not exactly equal, but like.
Okay, so we're identifying the fact that this chemical, the two little 3-atom chemicals, are turning into a 6-atom chemical. Yeah, are we seeing that that's kind of what's happening here in this reaction? When we get to the point where we are at C, we have 3 of these 6-atom chemicals. If we look at D, we still have 3 of the 6-atom chemicals. Yes, arsenic? They have the same. They have the same amount of product in C and D. They've just been changed like the area where they're sitting. And so that means that by the time we hit to C, since we don't change the amount of product by the time we get over here to D, that means that we must be putting D and making some of our Ds turn back into the 3-atom particles, and some of the 3-atom particles are still getting turned back into 2-atom particles, right? So, or 6-atom particles. So we're getting a back and forth exchange. The place where they are equal to each other, where they have the same amount of products and reactants, in this particular situation is when you reach equilibrium. But remember, you are not necessarily going to have the same amount of products and reactants each time. You are going to have an exchange that continues. The rate is going to be continuing to be the same as far as how much they exchange. Notice that we have 4 of our reactants there, 3 of our products. So they're not going to have the same concentration, right? They don't necessarily have the same concentration. All right. So that was arsenic. If we look at this table, or this chart, we can see that we have a reaction rate where we have hydrogen and iodine. These are our reactants. So hydrogen and iodine at the top of this chart are making our hydrogen iodide, okay? And that forward reaction means if it's steep, remember, if we have a steep part for our reaction rate, that we have a fast reaction rate. Things are happening quickly, right? So we've got a lot of product that's being made. And then in the reverse reaction, we have the exact opposite. Our 2HI, hydrogen iodide, is being turned back into the hydrogen and the iodine. But this slope is not as big, is it? This slope is much more gradual, which means the rate is much more slow, which means we are not making as much hydrogen and iodide as we're making hydrogen iodide. Okay, hydrogen and iodine we're making that much lower than we are making the hydrogen iodide. Eventually, we hit equilibrium where we have an equal exchange of how much one is making the other. But you should be able to see that we have a product-favored reaction here, where we have a whole lot more product because our forward rate was faster than our reverse rate. So by the time we get here, we're going to end up with a lot more HI than we have the H2 and the I2. The rates are now the same, but now we have a greater amount of product than we have reactant. Does everybody see that? Questions on that? Okay, so our equilibrium position is basically just saying that we're gonna, depending upon the chemical, we're gonna have a different mix of our products and reactants. If we have more products, we say that it is product favored. If we have more reactants, we say that it's reactant favored. Okay, sometimes you're gonna have about an equal amount of both, but we oftentimes will use these terms in chemistry. It's a product favored reaction. It's a reactant favored reaction. Okay, and that just is one way of saying which way the equilibrium position is shifting. Is it more to the reactants or more to the products? Now we have a few other ways of describing this. One of them is to say that it lies to the left. Okay, if it lies to the left, that means that we have more reactants that are formed because that's the left side of our reaction is the reactants, right? If it lies to the right, then we have more of our products. So if I say, hey, this reaction lies to the right, that means we have more products that are going to be made in this reaction than the reactants. So we just use some different terms sometimes to describe these different equilibrium positions. You're going to see another one here in a second that we also use. Okay. Now let's talk about what our equation is to describe an equilibrium. Our K is a value that we call the equilibrium constant. Notice that we have specifically a KEQ here. There are a few different types of Ks that we're going to talk about this year. This is one of them. We'll talk about a KSP. We'll talk about a KA, a KB. This is KEQ. This is the equilibrium constant equation. And this is the formula that we use to derive the equilibrium position, basically. This formula will tell us where we are with respect to how much of our products, how much of our reactants we have when we're finally hitting equilibrium. We take our chemicals A, B, C, D, those are the chemical compounds, and we're going to take them to the power of J, K, L, M. Those are our coefficients. So our coefficients become our exponents, and our compounds are going to be taken to those powers. So I'm going to take my products divided by my reactants. So my products here in this case are C and D. It's C to the power of L and D to the power of M divided by A to the power of J divided by B to the power of K. That number is going to be a number that just tells me where I am with regard to my equilibrium position. Am I to the right? Am I to the left? Am I product favored? Am I reactant favored? Remember that it's a relationship. That's what K basically is, telling me about my concentrations. I'm going to use concentration for my unit, molarity, for my unit for concentration. But when I come up with my final value for K, there are no units for my final value for K. And that's because K can have just a ton of different units because of all the different coefficients you could have. So this is all determined experimentally. So we have got to figure out that the K that we determined was done based upon doing some experiments and looking at our equilibrium position. So let's look at one other aspect of this, which I think sometimes is the most confusing part. And that is that the only thing that affects our KEQ is our temperature. You're going to see this come up, and it's going to affect your answers on some of these things. So pay close attention to this. KEQ is only affected by temperature. Now, that's assuming that we have all of our species being the same, all of our chemicals, right? So if I've already got my chemical reaction, the only thing that can change my equilibrium position is going to be my temperature. If I change the different chemicals, obviously you're going to have a different K because I have a different chemical. Okay, different chemicals are going to have different Ks. And so for the value of KEQ, it just depends upon the chemical you're dealing with and on the temperature. But if I'm talking about a chemical equation already, the only thing that can change that is temperature. And I think the reason that's confusing is we've talked about pressure, for instance, being something that might affect other types of situations. We might talk about Le Chatelet's principle and whether or not something is being affected by that. And you can have other things besides temperature for Le Chatelet's principle, but not for KEQ. All right, so if my K is greater than 1, I know that I'm going to have a product favored or a favorable reaction that's going to lie to the right. If my K is less than 1, I'm going to have a reactant favored reaction. It's going to lie to the left. It's going to be unfavorable as it's shown at that temperature. Remember that your size of K and the time are not related. I could have rusting, right? Let's say I have some iron that's turning into iron oxide. That might be a very, very slow reaction, but it might be very, very product favored. So ultimately, all that iron is going to turn into rust. So it's very product favored, but it could happen very slowly. So the time is not related to the K value. Time is determined by your reaction rate. We learned about reaction rate last chapter, and so that's a formula that we already have in our brains. Again, we didn't have to solve for it, but remember, we were able to figure out what the reaction rate is with a different formula. All right, so here's an example of a chemical formula and its K expression. I would take my products, my NO2, to the 4th power, and my products, H2O, to the 6th power, right? So it's 6th power because it has a coefficient of 6, 4th power because it has a coefficient of 4. My products divided by my reactants, right? And so in this case, I'm going to have my NH3, which is to the 4th power because of that 4 there, and my O2, which is to the 7th power because of my 7 there. So you just create this equation. You'll be given the values for the concentrations. You plug those all in, multiply them out, and you get your K. If it's bigger than 1, it means what? Favorable, product favored, right? If it's less than 1, it means reactant favored, okay? All right, so what would this K equation be for the reverse reaction? What would we need to do to figure that out? Let's go with gallium.
Flip it over and put like NH3 on top and O2.
Yeah, absolutely, right? Reverse this thing, flip that whole equation, and now we'll have the reverse reaction because now our products became our reactants and our reactants became our products. So suddenly this is now our reactant and that's our product. And so now we're going to have to swap that whole thing. And so now we'll have our NH3 and our O2 on top. And then on bottom, we have our NO2 and our H2O. Okay, so if I wanted to reverse that reaction, I just have to reverse our equation and flip that to an inverted equation. Questions on that? Okay. So it's important to note that the liquids and the solids do not end up in an equilibrium expression. If you notice this equation back here, I had gas, 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 gas. Well, if it was not gas, if it were a liquid or a solid, I would not include it in my equilibrium equation. I'm only allowed to include my gases and my solutions, my AQ components, right? My ions. Now, why is that? That's because that little chunk, for instance, of calcium carbonate at the bottom is a great source of calcium carbonate, but it doesn't change my concentration. right? My concentration that's in that container is going to stay the same because the dissolving part is at equilibrium also, right? And so there's no change in terms of what my actual compounds are going to be that are being made, like my calcium carbonate turning into carbon dioxide, right? And the calcium oxide. So this is not changing the overall equilibrium constant. The amount of liquid that I have in there, the amount of solid that I have in there does not change the equilibrium constant. It's just the amount of gas that I have, right? So that CO2 does change, and any sort of ions that I would put in there also, okay? That could change it. Okay, so that is probably important as we look at this question here. You should be able to write the expression for K. Let's see if you can do so. I'll call on you here in a second. Try to do it for both equations. I'll call on you here for the first one here in a short time. The L for the liquid.
It's an I.
Yeah, it does kind of look like an I. Yep. Products divided by reactants. Now let's get us up for your second one. For your first one. What is that? And what are we supposed to do with liquids? Not include them. All right, let's see what Moscovium has to say. What do you think about this first one? Yeah.
I said it was favorable. So greater than 1, K is greater than 1.
Okay, we don't know this for sure because we don't know our concentrations. So give me my K value first. How do I calculate K?
K is parenthesis H2 parenthesis 2. And then parenthesis O2. Parenthesis.
Good. So these are called brackets. So we use the term bracket there for those. But yeah, do we divide it by the H2O here?
No, it's a liquid.
Good. We do not divide it by the H2 on this one because it's a liquid. So this equilibrium constant, we don't know if it's bigger than 1 or less than 1, but you know, it depends upon the concentrations that we have in terms of molarity. But we could find out if we had some actual values. Our K for this one is going to basically be the same thing, but we are going to be able to divide it by our H2O this time because our H2O in this case is actually a gas. And so on this one, we can say that the equilibrium constant for this value is going to be affected by our water, whereas this one is not affected by the water, right? Because we could not include that one. So if our concentration here is bigger than 1, then this is going to end up being a smaller K than that K there. Okay, good job, Moscovium. Questions on that? Okay, so if KEQ is larger than 1, then is this product favored or reactant favored? Germanium is not here. How about iodine? Good. Larger than 1 is product favored. And the blank reaction is going to be favored. How would we state? Go to lead. Okay, the forward reaction is favored. Excellent. Good job. Then the yield is phosphorus. Okay, yield also means product. So high, right? So our product favored is going to be the same thing as like yield favored. So our yield should be high in this case. Good job. Then if we go to the other side of things and we say, hey, if KEQ is smaller than 1, then we'd say that it's reactant favored, it's favored in the reverse direction, and it is going to have a low yield, right? So it'll be the opposite of what the KEQ being bigger would be. Now let's look at how you would actually calculate an equation like this. This is what you might see on a test. It says the N2 and O2 are naturally present in our atmosphere at high temperatures, such as those found inside car engines. A reversible reaction occurs to produce nitrogen dioxide, a major component of smog. So if we have high temperatures, we can take the natural nitrogen and oxygen in our atmosphere and turn it into smog. We don't want that, right? But that's what happens. At 25 degrees Celsius, though, it says that KEQ is 0.855. We should be able to look at that number and determine if it's reactant or product favored. 10, what do you think it is? Why? Less than 1, and so reactant favored. Good job. Yeah, absolutely. So it's less than 1, it's going to be reactant favored. Oops, I thought I had that on the last slide. I guess not. Uh-oh. Okay, so reactant favored. Now, at 815 degrees Celsius, we can now calculate KEQ using these concentrations. So we're going to have to come up with our formula, right? So let's have gallium come up with our formula for this K.
2 or brackets.
NO. NO what?
2.
Good.
And then end brackets 2.
Good.
Over O2 or brackets O2.
Good.
Squared.
Uh-huh.
And then N2.
Excellent. Did you check to make sure they were all gases or aqueous?
I did not, but now I'm checking.
And they are, right? Good job. Okay, so now we got to plug in some numbers, right? So we're going to have to plug in our numbers for NO2. We're going to have to say, everybody get your calculators out, 5.56 times 10 to the negative third molar. And then we've got to square that. And then we're going to divide it by 2.0 times 10 to the negative 2 squared, right? And also divide it by 7.0 times 10 to the negative 2 molar. Once you've got that answer, let me know. All right, raise your hand if you got an answer. And arsenic, what do you got? Does K have units? No units. 1.1. Yes, good job. Now, There you are. Indium. Is this reactant or product favored? Because it's above 1. Great job. So this is a product favored reaction, a bigger than 1. So that means that we are going to end up with more products at 815 degrees Celsius. We're going to end up with more smog, right? The NO2. We're going to end up with more smog at that high temperature that would be inside that engine potentially. Okay? So if we can keep the temperature down, then we aren't going to end up with more smog, but at that higher temperature, we have more smog than we have the nitrogen and oxygen. Cool? Questions on that? Okay, good job, indium. All right, so let's look at this table here. First of all, let's just kind of understand what's happening. We've got some starting concentrations as we begin our experiment. Okay, and we've got 3 different experiments taking place. And we have 3 different concentrations that we're starting with in these 3 different experiments. And one of them, we're starting with an equal amount of the hydrogen and iodine concentration in moles per liter. And then in the other one, we're starting with all hydrogen iodide. We're starting with all product. And we're going to see what happens. And then in the third one, we're starting with all product again, but we have even more product. And we want to see what's going to happen after a certain amount of time. And I bet we can figure it out if we do the equilibrium constant expression. So if we calculate the equilibrium constant expression, we know that we have HI, right? Oops. Product, right? HI squared divided by our H2 concentration and divided by our I2 concentration. Okay, so that's our equilibrium constant. All we got to do is plug in some numbers. Let's kind of take a look at this. If I have a 1 and a 1, those are going to be 0 divided by 1. Then if I go over here, HI, that's a 1 on top, 1 squared. Okay. And then 0's on bottom. And then 1.5 on top. Okay, squared. And then divided by 0's there. So what do we see happening? What we see happening over time is at 490 degrees Celsius, once it hits equilibrium, then we have to plug in the actual numbers that we get for our experiment. And I want you to take note of something kind of interesting here, right? Our amounts of our concentrations for our hydrogen and our iodine are equal each time, okay, because of the ratio of the moles, 1 to 1. And we see that if we start with all reactants, we end up with more product. It's a product-favored reaction at 490 degrees Celsius, okay? And we can figure out what our K is at this one, and at this one, and at this one. What do you think we're going to come up with for our answer in all 3 situations? The same answer, right? Because the only thing that affects K is our temperature. It doesn't matter what concentrations we start with. Ultimately, we're going to end up at the same K value. Now, we might not end up at the same concentrations of each of them when we're finished, but we're going to end up having the same K value. And that answer, that K is going to be, oops, let's see, I think we have it on the other slide. Didn't show up on that one, apologize. And that K value is 45.9. So if we had plugged all these things in and we solved for K, in each example, using each of those different numbers, we would end up with 45.9. Product favored or reactant favored? Thallium?
Oh, reactant favored.
Because?
Product favored because it's bigger than 1.
Product favored because it's bigger than 1, right? Way bigger than 1. And so this is really product favored, right? You're not going to have very much of the hydrogen and iodine at all anymore. It's going to be mostly all hydrogen iodide, okay? So that's how we would do a problem like that. All right, so now you have been able to tell me what the reversibility of a change is and describe the conditions it depends upon. So let's go ahead and call on you, and you can help me put that into words. Tellurium. What is reversibility of a change, specifically chemical change, and what conditions does it depend upon?
The forward reaction is the same as the reverse reaction.
Okay, so forward and reverse reactions are present, and what kind of things do they depend upon?
Concentration, pressure, and temperature.
Yes, concentration, pressure, and temperature. Good job. All right. Dynamic equilibrium. Tell me what it means in terms of forward and reverse reaction rates. This is going to go to strontium.
For dynamic equilibrium, so forward reaction is basically when the reactants are turned into the final product, and then reverse reaction rates are basically when the product is like decomposing back into the reactants.
Okay, so yeah, you're describing the idea of a forward and reverse reaction, but I want to hear about dynamic equilibrium with regard to rates.
When the forward rate and the reverse rate are equal, the dynamic equilibrium is reached.
Forward rate and reverse rate are equal, and then tell me a little bit more about what dynamic equilibrium means.
It means the amount of reactants and products that are being produced are equal.
Okay, they are exchanging at that same amount. Are the concentrations of my products and reactants going to be the same?
No.
No. Good job. All right. Now we took a balanced equation and we constructed an equilibrium constant expression for it. And what do we turn our coefficients into in that expression 10? The exponents. Good. Yes. Our exponents. Our coefficients become our exponents. If I have a liquid or a solid, thallium, what am I going to do with that in my equation? I don't put it in my equation. Good job. And then, did I give you points? Did I skip that? Okay. I'm like, I don't remember. If I have a product and a reactant, which one goes up on top? Moscovium.
Products go on top, reactants go on bottom.
Excellent. And then what does my K value tell me? Lead. Not sure. What does my K value tell me? Germanium's not here. Iodine. Okay, what does that equilibrium constant mean? K is my equilibrium constant. What does it tell me? Okay. Okay, we find out K at equilibrium when the reaction rates are equal to each other, but it still doesn't tell me what it tells me. So I like where you're going, but we haven't quite got there. Let's go with fluorovium.
Tells the ratio of the mathematical product of the concentration of the substances.
Okay. In your own words?
It's that. It's kind of the words I wanted to use anyway.
Use them without reading.
It's because that mathematically it will reach the equilibrium, and that's like the. I want to say ratio. That's the word I just said.
The ratio of what?
When we solve it all with math.
Okay, good try. Not going to quite give that one to you. Polonium.
It's product favored or reactant favored.
It can't tell me if it's product favored or reactant favored, right? It tells me my equilibrium, starts with the P, position. It tells me my equilibrium position. where this reaction falls in terms of being product favored or reactant favored. It is a ratio, right? It's uses the mathematical equation to give us a ratio, but that ratio number, that K, is telling us if it's product favored or reactant favored, where the equilibrium position is. Okay? All right, good job, everybody. We did it. Woohoo!